Welcome to UV Physics Academy. So in this series, I'm going to discuss these quantum algorithms. First, I'm going to introduce two fundamental features which are used in most of the quantum algorithms. That is quantum parallelism and phase kickback. Okay, first let us start with this quantum parallelism. What is quantum parallelism? So this means it can execute multiple number of paths simultaneously. In most of the algorithms will be having the input like this. So here I will represent like this. That means we have n number of inputs there, n number of paths. Okay, and here we have this head mod gates. Let us suppose h tensor here n. So this means we have h tensor h like this. Okay, on each path the head mod gate operation is there. Okay, so then what about this output? That means these n number of head mod gates are operating simultaneously on the top n number of paths. So you will get like this. This is a 1 over root capital N. This is a summation x, where x is equal to 0 to n minus 1. And here we can take n is nothing but a 2 power n, where small n is the number of qubits. If you have an two number of qubits, then it capital N will be 4. That means 4 basis states will be there. Okay. So for example, we have 0, so 2. That means I have taken 2 paths. Then here we have h tensor 2. Okay. So then this is 1 over under root 4. This is the summation x is equal to 0 to 3 and sorry, here it is x. So if you expand this 1 over root 4, 0 plus 1 plus 2 and 3 like this. Now here I'm going to discuss one more most important point. Whenever you are solving this Dewey-Jones algorithm or Brainston-Wazirani algorithm, okay, so we'll be having one problem. That is, here we have all inputs are equal to 0, but sometimes we will write like this: the input is x, this is n number of qubit string. You can take this is a n number of qubit string. Okay, so now here we have n number of Hadamard gates operating simultaneously on this input. Okay, so earlier all are zeros, but here x may be anything, either 0 or 1. Then what about this? So here we will write this output as 1 over root n as usual, summation as usual, summation over x, sorry, I can't take x here because input already taken x. So this is, let us suppose, summation over z. Okay, here this is a z is equal to 0 to n minus 1. But here one phase factor will come, that is a minus 1 whole power. This is x dot z. So this is a very important and very important. So this is nothing but a phase, and this one x dot z is nothing but the binary dot product. If you understand this, then only you will understand the algorithms. In most of the algorithms will use this feature. So binary a dot product, and of course don't forget this is a modulo 2. I will explain what is this binary dot product, everything I will explain. So if it is all are 0 inputs, we will get the phase factor always a plus 1, plus plus. That's why here we are having all plus. But other than 0, if for example you have 110 or 111 like that, then some phase changes will be there, phase factors will be there. So that is nothing but minus 1 whole power x dot z, where x dot z is binary dot product. Okay, so now what is this binary dot product? For example, you have x equal to let us suppose x1, x2, x3, so on, okay, xn, and z equal to z1, z2, so on, zn. So both are n bit strings. So if you want to find x dot z, this is nothing but this is just a product, I mean x1 z1 plus x2 z2 plus so on plus xn zn. But remember, this everything modulo 2. That means once you have added all the things, whatever you are getting, you have to find the modulo 2. So for example, if you get a sum is equal to 2, then it is a 0. If you get sum is equal to 3, then it will be 1, something like that. Okay, so every time finding like this, it's not possible. Here I'm going to give you one small technique. It's a very useful technique. Okay, so that is a phase table I'm going to give you. Please listen. This is very useful, and with this table we can solve, I mean we can solve this, or we can understand the algorithms very easily. Okay, so here let me explain what is this. This is the phase table. Okay, I can take minus 1 whole power x dot z, minus 1 whole power x dot z. With this table you can find whatever the phase factor you want. Okay, right. So the technique is very simple. Please observe here. So this is if you have 0, you have to start with the plus plus. If you have 1 as LSB, okay, you have to start with the plus minus. And after that, next point is very crucial. First, let me start. Listen carefully. This is very important. So here I am taking 0 0 binary notation. I am taking. Okay, right. Now first starting one. Could you please check what is the starting one? 0. So you have to write plus plus. Next one is what? 0. Remember, if next bit is 0, whatever earlier you have repeated all the things again. I repeat, first one LSB is 0, then start with plus plus. If LSB is 1, start with plus minus. After that, again 0 came, then repeat all the signs again. That means plus plus. Okay, still not understanding. One more. So here LSB is 1, so that's why plus minus. Next bit is 0. I have to repeat the earlier signs as it is, no change. That is plus minus. Next one, see carefully. Here 0 plus plus. Next one is 1. Wait. If you get 0, repeat the earlier signs as it is, no change. If you get 1, multiply all the signs with minus. That means an extra minus will be there. Here plus plus, if you multiply with minus, this is minus minus. Still not understanding? Here 1, I have to start with plus minus, but again 1 came, so whatever earlier signs I have to multiply with minus extra. So minus plus. So this is the phase step. So what is this? Still I didn't understand. Okay, wait. So here I am taking this is x and this is z. Now for example, if you want to find the phase factor of minus 1 whole power 3 dot 2. Actually we have x dot, one second. So here phase minus 1 whole power x dot z. So for example, if you want to find minus 1 whole power 3 dot 2, which is nothing but minus 1 whole power 2 dot 3. So binary product. Actually how you have to do? You have to make the binary dot product and modulo 2 operation you have to take. So here with this table, we'll get directly. So that is, see carefully, 3 dot 2. Here it is a 3 and here is 2. So this is minus. Of course, minus 1 if you want, you can write. Okay, so this is minus. And still, if one more, minus 1 whole power 3 dot 3. Of course, here it is a plus. So that's why a plus. Plus 1. So minus 1 whole power 1 dot 2. Okay, so here is a 1 and here is a 2. So it is plus 1. If you want to check with the original dot product, binary dot product, let us check this. 1 dot 2 equal to actually 0 1 dot 1 0, which is nothing but 0 plus 0, which is a 0. Okay, so like this we can do. Now let us, if we are still not understanding, let us take 3 qubits. So here we have taken 0 0 0 0 1 0 1 0. Let me write this. So I feel it's very easy to understand that phase factors with this table. Okay, right. So first here we have 0, that's why start with plus plus. Next 0 came, repeat the earlier as it is. Next again 0 came, repeat the earlier signs as it is. Repeat all the earlier signs. If 1 came, multiply all the earlier signs with 1 minus extra. So here 1 plus minus, 0 came, plus minus. Now again 0 came, all the earlier signs as it is, please write. Okay, next one 0 plus plus, 1 came, minus minus, again 0 plus plus, minus minus. Next here 1 plus minus, 1 minus plus, 0 plus minus minus plus. Here 0 is there, plus plus. Again 0 came, plus plus. 1. So 1 came means you have to multiply with the minus. Minus, minus, minus. And the next one plus minus, and a 0 plus minus, 1 extra minus, minus plus minus plus. And here plus plus, next 1 minus minus, next 1 minus minus plus plus. Whatever you have, all the previous signs you have to multiply with the minus. Next here plus minus, again 1 minus plus, again 1 minus plus plus minus. Okay, so now let us check this minus 1 whole power 7.7. So 7.7 here it is a minus, so it's minus 1. If you want to check with original dot product, binary dot product, 111 dot 111. This is nothing but 1 plus 1 plus 1, which is a 3, and if you take modulo 2 operation, so this will be 1. So then minus 1 whole power 1 is nothing but a minus 1. Okay, so like this you can get the phase whatever you want. So that is, for example, one more, let us find 6.5. So originally if you want to find, this is 110.101, so which is nothing but 1 plus 0 plus 0, which is nothing but 1. Now in this table, here is a 6, sorry, here is a 6, here is a 6, and here is a 5, this one minus 1. So I hope this is useful to you. Okay, so still if you are having any confusion, you can try this next to 4 qubits also, you can try. And now I'm going to discuss a small technique, okay, to get the phase factor. Okay, so for example, if you have very big numbers, let us suppose we have, right. So I will come back to these tables again because very useful tables. Okay, so okay, so the meanwhile I will tell you one small technique to find this phase factor. So for example, you have some big numbers, let us suppose minus 1 whole power 12.15. Just I have written in a decimal notation. Okay, no need to get tension, right? So how to find this? Actually it is a 12.15. So first let me write in the binary notation. So this is a 1100, because 8 plus 4 dot 15 means all ones only, so 4 qubits. Now this is nothing but 1 plus 1 plus 0 plus 0 and modulo 2 operation, which is equal to a 0. Then we can write minus 1 whole power 110 dot 111 is nothing but a plus 1. So instead of writing this binary dot product, I will tell you a small technique. Now carefully observe here. This is the another way to get this phase factor. So here we have minus 1 whole power 12 dot 15. I am taking a decimal numbers only. Now what you have to do is, you please write this at 12 as 4 qubit states. 4 qubit states means you can take like this. I hope this technique, the same technique I followed earlier quantum circuits also, while I am solving quantum circuits. 1, 2, 4, 8. Now how you will get to 12? That is 8 plus 4 plus, sorry, let me write uh, 8 plus 4 plus 0 plus 0 dot, and this 15 you have to take all 8 plus 4 plus, sorry, 2 plus 1. Now what I am doing is, just I am counting how many common on states. I am not bothering about off states, I am counting number of on states. So this is nothing but minus 1 whole power number of common on states. So don't consider zeros. Okay, right. So now here 8, 8, 1 common, 4, 4, 2 common. So 0, 2 not common. Here 0, 0 is there, don't take it common. Only we have to take on states. On state means it's a value 1, 2, 4, 8, these numbers. So here 0, here 1, cancel. So I'm cancelling that off states, and I am cancelling that not common states. Then tell me how many number of common on states are there? 2. So that is minus 1 whole square, which is plus 1. You'll get the same phase. Let us try one more. So for example, if you have minus 1 whole power 30.10. So first I'm writing in the decimal notation, decimal numbers. If you want, you can write the binary also. Let me find with my method, and after that we will do with the binary dot product. So here we have 13, that is 8 plus 4 plus 0 plus 1 dot 10, that is 8 plus 0 plus 2 plus 0. Now let us just count how many commons are there. Okay, 8 common, 4 not common, 0 not common, 1 not common. So you have only one common. So number of common on states, I repeat, on states. So number of common on states, on, please be careful. Okay, so here I got number of common on is a 1. So that's why this is nothing but minus 1 whole power 1, you will get a minus 1 factor. Let us find with the binary dot product. So here this is a 13, that means 1 1 0 1 dot 1 0 1 0. So this is nothing but 1 plus 0 plus 0 plus 0, which is 1. Let us try one more. Minus 1 whole power, let us suppose take a 12.13. So this is x and that is z, like that, x dot z. Okay, okay, fine. So this is nothing but 8 plus 4 plus 0 plus 0, because of 4 qubits, and here 8 plus 4 plus 0 plus 1. So you have to take only common. So here 2 common, these two are not common, that's why minus 1 whole square, which is a plus 1. Now if you find the dot product, 1100 dot 1101, which is nothing but 1 plus 1 plus 0 plus 0 and modulo 2 operation. So this is plus, sorry, 0 you will get, 0 you will get. So minus 1 whole power 0 is nothing but a plus. So this is what I am saying. Maybe it will be useful or not, I don't know. Okay, so if it is useful, take it, otherwise leave it. And now let us come back to this tabular form. This is a very crucial and very important tabular form. Okay, so please wait. So with this table, we can find the output very easily. Okay, so for example, here I have x2, that means 2 qubits. Okay, so as per that formula, what is this output state? Output state, that is a 1 over root 4, because 2 qubits are there, and summation minus 1 whole power x dot z. Okay, so this is a z, where z is equal to 0 to 3. So for example, I would like to find h tensor 2 operates on 3. So you need not to find these phase factors separately. So directly please take this. So that is plus minus minus plus, that is 1 over root 4, 0 minus 1 minus 2 plus 3. Still one more. If you are not understanding, this is a h tensor 2 operates on 2. So this is 1 over root 4. So I request you just to go to this 2. We have signs plus, plus, minus, minus. So this is nothing but 0 plus 1 plus 1 minus 2 minus 3. Let us take the 3 qubits. So for example, if you have here, if you want to find h tensor 3 operates on 5. Okay, so most of the quantum algorithms we will use this type of operation. So here 1 over root 8. So what are the phase factors? This table will give you all the phase factors, and please go to this 5, this one. Okay, plus minus plus minus minus plus minus plus. So just take that, and now it is 1 over root 8. So here we have 0, next minus minus, sorry, I'm sorry, first let me write this plus minus plus minus minus plus minus plus. Just for understanding I'm writing, later you need not to write. 1 over root 8, so this is a 0 minus 1 plus 2 minus 3 minus 4 plus 5 minus 6 plus 7. Most of the algorithms I will solve by using this type of techniques only. So if you attend all that lectures of that quantum algorithms, you understand this method. So this is very useful and okay, and very easy to write. Okay, right. So let us discuss about this phase kickback. This is the another most important feature. So what this phase kickback? What is this phase kickback? So it moves the information of f of x, some unknown function, or some function, from a target register to data register. So here this is the target register, we can take, and this is the data register. So how it is transforming? Let us take this C naught operation here, and let me explain. So here how you got this minus 1. So for example, this is the 2 qubit 2 qubit 2 qubits, and this is x, and here we have 1, the head mod operation is there. So h operates on 1, you will get minus state. So here the C naught is as usual. So what is this? Here the input is x 1, and now we are operating this This is the identity here. Nothing is there means identity we can take. So wait a minute. I tensor H. So I operates on X, that is X only, and H operates on 1, you will get minus. So let me write this value. This is nothing, I mean this state, that is nothing but 1 over root 2. So X here I am writing, sorry, X, and this is a 1 over root 2. So this is a 0 minus 1. Okay, so diagonal basis actually, that is minus is nothing but diagonal base. 0 and 1 are Z basis. So now here finally we got X 1 over root 2, 0 minus 1. Let me explain with this example. What is this phase kickback? And here we have C naught operation then. So here who is the control bit here? This is the X. Okay. So here we have two possibilities. If X is equal to 0, so no operation. If X is equal to 1, then not operation will be there. Okay. So that means some change will be there. So if X is equal to 0, this will become 0 as it is, because the control bit is 0. So then this won't be operated. So that is as it is. We can take X 1 over root 2, 0 minus 1 as it is. If X equal to 1, that is the control bit is 1, then the target will be flipped because this is C naught. So here this will become X 1 over root 2, carefully observe. Here we have this one 0 and 1. So that will be flipped, that means 1 minus 0. And this can be written as minus 1, okay, X, okay. So this is a 1 over root 2, 0 minus 1. So finally we can write this as minus 1 whole power 1, because here X is equal to 1. So minus 1 whole power 1, of course here I am writing X only, and after that minus. So if you want to write more generally, so this is nothing but this minus a state as usual, this initial state whatever we have, and this here will get minus 1 whole power x. So the output state is nothing but minus 1 whole power x minus. So this phase factor, this one minus 1 whole power x, that is transferred from this target resistor to data resistor, because that minus we got because of this head mod operates on 1, and after that C naught operation is there, which is controlled by this X. So here this is the phase kickback small example. If you want to generalize this, so if you want to generalize this, for example, let me take like this. Here we have two qubits. Let us say this is X, and let us say this is a minus, and let me write this one more time. So this gives minus 1 whole power x, and this is minus 1 as it is. If I take more generally some function is there, let us suppose f, and here we have x, and this is a minus, this minus is as it is, minus state is as it is, minus 1 whole power f of x, sorry, f of x. So this factor is transferred from this target resistor to a data resistor. So this is what we are discussing. This is what we are discussing about this phase kickback. Okay, so it transfers the information of that function from target resistor to data resistor. Okay. Right. So once again, here was first what we have discussed. This is a quantum parallelism. That means how these n number of multiple inputs. We have n number of multiple inputs, and these n number of gates are simultaneously operating on that inputs. and after that I have given some tabular form which is used to find the phase factors, okay, that binary dot product. And after that, this again, these tables are very useful if you want to find this head mode operation on that a particular state. If you want, you can find. So I have tried this 4 qubits, 5 qubits also tried, okay. So if you are facing, if you are getting any different answer, so please let me know, okay. And after that, a phase kickback, which is transforming the information from information of f of x from target register to data register. And I have explained this. This is the final result. Okay, so that's it. In the next lecture, we will discuss quantum algorithms. That is, two protocols we'll discuss.